Before starting, I want to thank you all of this organization of the TXRF Club, and also to give me the opportunity to share with you my experience on the application of TXRF in the case of geological samples. In fact, in the presentation of today, I will explain or present some of the results that we have obtained during the last 10 years in our group. So I will start I will start saying that in most geochemical studies, it's necessary to have elemental information about the different types of geological samples. One of the most commonly used techniques for such purpose are ICP-based techniques, because as you already know, they have excellent limits of detection. And also they can give us multi-elemental analysis. However, the main drawback regarding the geochemical samples is that the solid samples sometimes are difficult to get digest. So this is one of the main limitations of these techniques. For the reason, another type of techniques that are commonly used are conventional XRF systems. The main advantage of these techniques is that you can analyze solid samples with a simple sample treatment, and you can get also multi-elemental information. However, the main limitation, as you know, are the limited sensitivity for some trace analysis, and also that they cannot be applied for the analysis of liquid samples without a sample treatment. So in the slide, you can see some of the analytical capabilities that can be of interest in the analysis of geological samples regarding the TXRF, including, for instance, that with this technique is possible the analysis of both liquid and solid samples, sometimes with a simple sample treatment. You have also multi-elemental and screening information. In the case of mass-limited samples, they can be used because due to the microanalytical capability, and usually we have adequate sensitivity for the analysis of traces. In the next slides, I will present you some of the applications of this technique in the analysis of geochemical studies. The first one is the element of trace at trace concentration levels in soils and sediments. The first case of a study was the determination of selenium concentration in volcanic soils. This study was performed during my postdoc stage at the Atom Institute in the group of Christine Astrelli 10 years ago. And at this time, I was interested in determining very low concentration levels of selenium in soils, because this element, it has a very narrow range between the safety concentration and toxicity values. First of all, I perform a bibliographic search to see the most commonly used techniques for the determination of this element in this kind of samples. And I realized that the most commonly used were atomic spectroscopy techniques with previous sample treatment. And I found also some paper regarding the application of conventional XRF, but as you can see in the table, in this case, the limits of detection were not adequate. So we decided to try to evaluate the possibilities of TXRF for the determination of selenium in soils. In this study, we use a reference material that it contains only 1.32 ppm of selenium. First of all, we evaluate the possibility of the analysis, the direct analysis of a soil suspension. Here you can see the parameters that we use for the preparation. We weigh 20 milligrams of soil, we add 1 milliliter of Triton 1%. And in this case, we use as internal standard germanium, because we realize that the soils contain already gallium and yttrium. So we can not use these elements as internal standard. However, using this approach, the limits of detection for selenium were around 1 ppm, so it were not adequate to quantify very trace levels. So we decide to try to digest the sample and then make a direct analysis of the digest. For the digestion, we use a standard method, the IPA method 3051, and then after obtaining the soil in a liquid form, we analyzed it. And as you can see here, the main problem was the high iron peak that it was present in the spectra. That limits the limits of detection for selenium around 0.75 ppm. So in order to try to decrease this limit of detection, we decide to study two different approaches to decrease the iron amount in the soil digest. The first one was a chemical approach. In this case, we add to the soil extract a solution of hydrochloric acid to form the iron chloro complex that it was removed from the soil extract, extracting this complex with ethyl ether. Another approach that was a physical one was the introduction of a chromium foil of 10 microns between the sample and the detector to try to absorb the iron before arriving the detector. In this case, using both approaches, as you can see in the slide, we obtain a clear reduction of the iron peak around 90%. We reduce also the limits of detection for selenium around 0.5, but still were not adequate to quantify this element at 1 ppm level. So finally, we decide not to remove the iron, but to extract the selenium from the soil digest. In this case, we use a microextraction procedure, is the one that you can show in that is shown in the slide. In this case, we add a mixture of ethanol, carbon tetrachloride, and APDC to the soil extract. The chemical basis of this extraction is that the APDC form a complex with the selenium that is extracted in a small volume of the organic solvent. Then these few microliters of organic solvent can be directly analyzed by TXRF. However, this procedure is only valid for selenium-4, so to obtain information about the total selenium before applying it, it was necessary a reduction procedure. Here you can see the benefits of using this microextraction. On the one hand, you can see the clear reduction of the iron peak, and in the other side, the improvement of the selenium peak and also the limits of detection that in this case was below 0.1 milligram per kilo in the soil. For the quantification, we try to prepare a set of aqueous selenium standards, but we realized that the selenium extraction in soil digest was lower than in the case of aqueous solution. So for quantification purposes, we need to use a standard addition. Using this procedure, you can see that we have finally very good results for selenium quantification in soils at very low concentration levels. Here in the table is a summary of the limits of detection obtained using these different sample treatment approaches. And the point is that you have to select the best procedure according to your application and of course to the concentration level that you are interested in. Another case of a study of the application of TXRF for trace element determination is in this case the determination of trace amount of bromine, in this case in agricultural soils that were previously irrigated with regenerated wastewater and fumigated with methylbromide pesticide. The expected concentration values in this case were in around milligrams per kilo, so we evaluate the potential use of suspension and TXRF analysis. Here you can see the procedure that we follow, but first of all, we evaluate the influence of the soil particle size to prepare the suspension. And we realize that we only obtain good results in comparison with energy dispersive if the soil sample was properly in a proper particle size, that in this case was 633 micrometers. We evaluate also the influence of the soil amount, the dispersant agent, and the deposition volume. And finally, we prepare the suspension by weighing 20 milligrams in 1 milliliter of tritol, and then with the sample deposition volume of 10 microliters. We apply this procedure analyzing a set of different reference materials of soil and sediment matrix, and the quality of the results that we obtained were acceptable for our purpose. And you can see that the limits of detection, that it was around 40 ppm, were also adequate, taking into account the background of bromine in soils. Finally, we apply the procedure to different soil profiles. Here, as an example, you can see the spectra obtained for a surface soil sample. And here you can see the concentration of bromine at different points of the soil profile. From this study and the TXRF results, we can conclude that the bromine was accumulated more in the upper layer of the soils, up to a depth of about 30 centimeters. And finally, the last example of this was we apply also suspension and TXRF analysis, in this case to study the metal dispersal, lead, zinc, and cadmium, in a mining area that was located in the northeast of Spain. We performed this study in cooperation with the group of Laura Borghese in Italy. Only to say that in this study, we focus mostly on the comparison of two systems, two TXRF systems, one with a molybdenum X-ray tube and the other one with a tungsten X-ray tube. And we focus also in the best quantification approach. Regarding the instrumentation, we saw that the limits of quantification obtained using the preparation that is shown in the slide. We obtain better limits of quantification for lead and zinc using the molybdenum system, but the limits of the quantification for cadmium were better in the tungsten, because in this system we can determine the cadmium using the K-alpha line. Regarding the quantification procedure, first of all, we apply the conventional internal standardization with the addition of gallium or palladium as internal standard. Using this procedure, the recoveries that we obtain for cadmium, lead, and zinc were around 70% that were not useful for our purpose, mostly due to the presence of matrix effects. So finally, we decide to test another approach that was internal standardization, but with the correction using a set of real soil samples previously characterized by ICP, in order to decrease these matrix effects. However, in this case, before applying this, we realized that the values that we obtained by digestion and ICP OS were of enough quality, and for that we analyzed two reference materials. Using this approach, we improved the recoveries up to 90–95% that were okay for this kind of studies. Finally, we evaluate also the use of an external calibration using a set of synthetic soil samples. In this case, we pick up an uncontaminated soil sample, and we add different amounts of the analytes of interest. However, this procedure was okay, for instance, for cadmium that is not present usually in the soils, but in the case of elements that were already present in the soil used to prepare the calibration standards, such as zinc, was not okay because we have already a quite high value of this element. So finally, we decided that the best way was to use this quantification approach. Once evaluated the method, we apply it to study the lead, zinc, and cadmium content in different points in the mining area. We pick up some soil in the mine, in a dump. Here you can see me, in this case, the day that we were in the mining area, and also 2 locations far away from the mine, that it was a path, and also some vegetable gardens that were placed around 2 or 3 kilometers down to the mine. Here you can see the results that we obtained. And as you can see, in most of the locations, the concentration, the metal concentrations determined were over the limit of agricultural soils according to the Spanish legislation, and in some locations even to the limit of industrial soils. So we can realize that in this case we have quite dispersion of these elements in this mining area. Another interesting application of TXRF can be the element determination in water samples and also extractant solutions. Coming back again from selenium, sometimes it's also useful to know information about the potential selenium leaching from the soils, for instance, or to check the presence of this element in different types of waters. So we evaluate the capabilities of TXRF specifically for the determination of selenium in rain, groundwater, and thermal water samples, and also in some extraction solutions that were used, for instance, to evaluate the potential leaching in acid-rain soil interactions. As expected, in the case of groundwater and rainwater samples, we were able to determine selenium with very nice results at low concentration levels using a simple deposition of 10 microliters of sample on the reflector. However, in the case of thermal waters, for instance, we have more problems because some of these waters contain a lot of bromine. And as you can see in the spectra, the bromine is overlapping the selenium peak. So we make a study in the lab and we realize that when the concentration of bromine increased, the selenium, the detection limit for selenium was increasing. So for instance, in a water containing only 1 ppm of bromine, the limit of detection was 3 ppbs, but if the bromine content was 50 ppm, the limit of detection was 25 times higher. We evaluate also the limits of detection for acidic extractions. In this case, we simulate the acid-rain interactions, putting in contact the soil with a solution of sulfuric acid. In this case, we realize that in the obtained spectra, we have a high amount of zinc that also limit the limit of detection for selenium at around 7 ppbs. We evaluate also the limits of detection for using hydrochlorine extraction that is commonly used to simulate the bioaccessibility in the stomach. And in this case, the limit of detection was even higher, mostly due to the presence of high amount of iron. And finally, we evaluate also the limits of detection in 2 basic solutions that are commonly used to evaluate the selenium associated to organic matter in the soil. As you can see in the spectra, the background using these extractions were quite high and the limits of detection were around 10 ppbs. So here in the table, you can see that for the analysis of ground on rainwater samples, the limits of detection are really low, but for the analysis of other types of water or leaching solutions, the limits of detection can be really high. So before doing an experiment, of course, it is useful to try to make a previous study of the limits of detection that we obtain. Another interesting application of TXRF can be, for instance, the monitoring of adsorption and desorption processes in lab-controlled experiments. Here, in this first study, we focus also in selenium. In this case, we want to evaluate, to understand the selenium absorption in volcanic ashes. And for that, we perform some laboratory kinetic studies. The main problem of this was that we did not have a lot of fresh volcanic ash to perform the experiments. So for us, the use of TXRF was really nice because of its microanalytical capability. In this case, you use 150 milligrams of volcanic ash. Then we put in contact this sample with a synthetic rainwater containing selenium. Then we mix the mixture and we extract a liquid of 50 microliters at 7 times to monitor the selenium absorption to the ash. And then we add for one of each of these liquids the internal standard. We deposit 5 microliters and we perform the TXRF analysis. Using this procedure, we were able to see, for instance, that the selenium absorption depends on the type of volcanic ash, and also it was also depending on the pH of the raining solution. Another benefit of TXRF was that we obtained for each of these fractions information regarding all other elements, and we can study also the behavior in comparison with selenium. And we realized, for instance, that when the selenium was absorbed in the ash, the iron was dissolved. More recently, in 2016, we apply a similar approach, in this case, to evaluate the absorption of silver nanoparticles in soil samples. Here is the experimental approach that we use. We weigh 1 gram of soil, we put in contact with a solution containing the nanoparticles, then we mix the mixture and we remove a liquid at several times. And then, because we can analyze with TXRF liquid and solid samples, we monitor the silver content in the liquid as well as in the soil after the adsorption experiment. Regarding the monitoring of selenium absorption, as you can see over time, it was not selenium, it was silver. As you can see over time, the silver content is decreasing, and this is because it is absorbed to the soil. We compare also the silver concentrations with ICP-OS, and we find that there were not statistical significant differences. So we realized that we can use TXRF for this purpose. Then, from the soil resulting of the absorption process, we dry it, and then we prepare a suspension. As you can see in the spectra, you can see that the silver is adsorbed on the soil in comparison with the soil before the absorption process. And here you have the information about the amount of the silver that it was monitored in the soil fraction. And as you can see, we obtain much better results when we use digestion and TXRF analysis if we compare with ICP-OS measurements. And finally, only to say that the TXRF can be also useful in the case of speciation studies. Coming back to selenium, in addition to evaluate the total concentration of selenium in the extracts, sometimes it is important also to specifically determine the inorganic species of selenium, in this case selenium-4 and selenium-6, because they present different toxicity. In this case, to do this, we apply the same microextraction procedure that I discussed before. In this case, we apply to the leaching solution a mixture of ethanol, carbon tetrachloride, and APDC to form the complex of selenium APDC that it was extracted with the organic solvent. In this case, we get information about the presence of selenium-4. If we perform here a reduction procedure before doing the microextraction, we will have information about the total selenium present, in this case, in the leaching solution, and if we calculate the difference between the total selenium and the selenium-4, we can get information about the presence of selenium-6. We apply this procedure, and here as an example, you can see the spectra of a leaching solution directly applying the microextraction that is shown in gray color. In this case, we cannot see the selenium peak, so this means that the selenium-4 was not detected. Then we perform a reduction step and we apply again the microextraction, that is the black spectrum. And in this case, we see that we have a selenium peak that in this case, it was 7 ppbs of the total selenium. So with the difference, we can conclude that most part or all part of the selenium in this leaching solution was in the form of selenium-6. The result was also confirmed by HPLC-ICP-MS. And finally, the last example that I want to show you is the study that we performed in 2018. In this case, we were interested in a study the transformations that gold nanoparticles can suffer when they are introduced in the soils. As you know, metallic nanoparticles are emerging contaminants that can be introduced in the environment. And sometimes when they are, for instance, in contact with soils, due to the soil matrix, these gold nanoparticles can be transformed to the ionic forms. For this kind of studies, of course, we will need a method that we can quantify, for instance, the ionic silver in presence of ionic gold in presence of nanoparticles gold, because if we analyze directly the resulting solution, we will have information about the gold, the total gold in the sample, but not for the specific forms. For the reason, we make first a specific extraction procedure to isolate the gold in ionic form from the soil extract. As you can see, in this case, we use a cationic surfactant that was able to extract the ionic gold, that it was in cationic form, and then this complex was extracted with the chloroethane and analyzed directly with the TXRF. Using this approach, the limit of detection for gold was really nice, below 0.1 ppb, and we obtained also a good linear range and a good precision of the results. We also demonstrate that we have a selective extraction of gold-3 in presence of silver nanoparticles, because as you can see, we analyze different mixtures containing different amounts of silver nanoparticles, and in all cases we can quantify in a good way the ionic gold. And finally, we apply the system in an experiment to study the potential dissolution of gold nanoparticles in the soils. For that, we put in contact 500 milligrams of soil in a solution containing gold nanoparticles. We mix this for 12 hours, and here, this is not good. This is not 12 hours. Sorry, it's different times, and then we evaluate the study of the liquid in the solution to evaluate the presence of gold. As you can see here in the figure, the amount of ionic gold over time was increasing. That this means that the nanoparticles that were adsorbed in the soil are transformed to the ionic form. So to conclude with this talk, I only want to say that the TXRF can be a good analytical tool in geochemical studies, dealing with, for instance, elemental determination in mass-limited samples, or in solution resulting from absorption laboratory studies that usually you have a very small amount of volume to be analyzed. Also can be of interest as a fast, simple, and sustainable analysis of solid samples. Of course, if the quality of the results it is enough for your purpose, and also it could be good for speciation analysis if it is combined with microextraction strategies. Finally, I want to thank again to the TXRF journal group and also to Ursula, the research colleagues that have participated in these studies, and to you for your kind attention. And the last slide is only to remember that there is a special issue about development and application of X-rays in metal analysis of soil and plants in the agronomy journal, that is an open access one, that we have extended the deadline for submissions until June 2022. And now, yes, I'm finished and it's time for discussion.
Thank you so much, Eva, for this very nice, interesting talk and this great overview of all you have done on the soil analysis. Questions, please. I see some faces already.
Hello, madam. Myself, Kaushik Sanya. I have one question regarding that micro extraction. So my question is, during that micro extraction, what is the volume ratio that you generally use? Suppose you want to extract some particular elements or some particular species from some certain volume. So how much volume ratio that is you generally use?
It's difficult to give you exact number because I cannot measure, but I did some tests, and I think that with this particular application, it goes around 20 or 25 microliters.
So,
but then I didn't analyze all this volume. Always I analyzing 5 or 10 microliters.
And one question here, during that micro extraction, you use some kinds of micro syringe. So is it necessary to use the micro syringe, or we can use any kinds of small tip to inject that extractor into the solution?
Usually, yes. I'm using a micro pipette, but with a very low volume. Now I cannot remember the range, but I think that is up to 5 micro or 10 microliters.
5 to 10 microliter, but is it necessary to use the micro syringe? Because
yes,
it is necessary.
Yes, sorry, yes.
Thank you, madam.
Yeah, you are welcome.
Thank you, Kaushik. Giacomo, I think, has a question.
Yeah, I have a question for Eva regarding the speciation of selenium. Okay. I probably missed what was the limit of detection for selenium in that case was.
let me, one moment, let me think, because I presented a lot of data. Now I think that in this case, yeah, it was after the pre-concentration. Yeah, I think that it was because we were able to detect and quantified 7 ppbs. So I think that it was around 1 ppb.
1 ppb. Okay.
Yeah.
Okay. Thank you.
1 point something. Yes.
Yeah. Okay. Thank you.
Sangeeta, please. Yes, go ahead.
Hello, madam. Hope you remember me.
Yes, yes, of course.
Madam.
I remember. Yeah, from
yeah. So really very nice presentation. Actually, I just returned from office, and in the office we are not actually allowed to assess this meetings. So I just joined the last part of your meeting.
But I think Ursula, I think that she can follow through the YouTube channel.
YouTube,
no?
yeah, I will definitely do that, madam. Yes, okay. I have one doubt, madam. You have done some measurement in sulfuric acid medium.
Yeah.
So how did you do the sample preparation?
Well, in this case,
it is very difficult to dry that.
Yeah, but look, this is not a concentrated sulfuric acid solution. It was to simulate the acid rain. So now I cannot remember the concentration, but it's a dilution. So I didn't have problems to dry on the reflector.
Okay. Because we are doing some measurement,
yeah,
in which the concentration of sulfuric acid is almost to 50%. So we are having some problem in drying that sample.
Yeah, but no, this was not the case. It was much more diluted.
But can you suggest something, madam, like how we can do it? Is it because we have to heat it to high temperature? So in TXRF, is it
because you are using a hot plate or how?
Yeah, hot plate. Yes.
So, the only thing is because with the vacuum, I think that you will not improve really this, and you have to be sure that is dry, because then you can also damage the detector with the
acid,
the vapors and things like this.
Vapors of the acid.
Madam, I also think the dilution can also maybe reduce that boiling point. That maybe dilution, if our concentration that we want to probe is very high, then we can dilute it 10 times. Then it can help, as you have analyzed some samples where the sulfuric acid concentration is very low.
The problem of dilution sometimes is that if you have very low concentration, then
that is the thing.
Yes.
If you have high
you
concentration,
have to have a compromise between these. Yeah.
Okay. Thank you, madam.
Yeah, you're welcome.
Thank you. Are there more questions? I have a question toward the determination of the bromine. So what precautions, you might not have mentioned it during your talk, do we have to consider fixating the bromine so that it doesn't, evaporate in one or the other species?
This is this is a good question, and here I only presented the determination of bromine in the soils as a suspension, and the results that we have in this case of the reference materials were quite nice. So in this case, I didn't detect any problem, but also we perform extraction of the bromine in bromide, using water, and then we compare our values with the ones obtained with ionic chromatography. That is the standard technique that is used in this kind of studies. And we also obtain very nice results. So I think that the problem of sometimes evaporation, it also depends on the concentration level that you have. If the concentration perhaps is quite high or is adequate, this effect is not so critical, I think, because I was also surprised that the results were quite agree very well with the other. Yeah.
So then I have a follow-up question. Do you know for the soil which species is present of bromine in the soil? So you have mentioned the pesticides, the methyl bromine, but that probably changes in the soil or not? Do you know?
Yeah, in this case, we were looking for a bromine, that the anion, the anionic
bromide, okay.
form. Yes, bromine, yes.
Thank you.
Yeah, you're welcome.
Other more questions?
Hello.
Hi.
Good evening.
Hello.
Good evening to everybody. Yeah, can you hear?
Yes.
Yes.
Okay, so I have one not questions, I would say. I want to have your comment. What do you think about the chemical activity of gold nanoparticle? Because gold is very chemically is not so active. So what do you think?
You mean, can you repeat me about, you mean about the reactivity
of chemical reactivity of gold nanoparticle?
Of the gold?
Yeah.
Yeah, okay. I'm not an expert of this. In this case, we have been working with nanoparticles in the last couple of years, more or less. And we have more or less focused on the development of analytical techniques for the discrimination of the nanoparticles and the ionic form. But as far as I know, with our experiments, for instance, if you remember that one of my last slides, the nanoparticles, once they were included in the soil, part of them are transformed into the ionic form. And we have made also other experiments to verify this in other kind of nanoparticles. For instance, the silver nanoparticles are also ones of special interest nowadays. And we realize also that once in the soil, the nanoparticles are transformed to sulfur compounds. So yeah, I think that more research is needed in this sense in order to determine what these emerging contaminants will or can affect once they are introduced in the environment, not only in soil, but also in water or in other compartments.
Okay, fine. I think this is good. So it is good.
Sorry, and also another thing that I did not discuss in this presentation, but also not only the type of nanoparticle, but also it is influenced the size of the nanoparticle and also the covering of the nanoparticle. So there are a lot of effects that can be of interest in this kind of studies.
Oh, this is what I wanted to ask, but it is already explained. That's fine. Okay.
Yes.
Thank you very much for the nice presentation.
Thank you.
Thank you.
Giacomo?
Yeah, and here again. I have another question regarding the iron removal from soil using.
Sorry, Giacomo.
Yeah. Can you
I don't
hear
know
me
what
now?
happened, but
Yeah. Can you hear me now? Okay, yeah, that's perfect. I have another question regarding the removal of iron from soil by using hydrochloric acid and ether. I missed why you gave up with that and then you prefer to consider the selenium.
Because I use these, you mean?
Yeah. No, I mean, what was it successful or not? Because then you tried to.
Yes. As you see in the spectra, the iron peak was removed around. I think that it was 80 or 90%, but still, then the limit of detection for selenium was also decreased, but it was not enough for our purpose. That was the quantification at 1 ppm level. So finally, I decided not to remove the iron, but to remove the selenium for the matrix, because in this case, I was also able to pre-concentrate. And finally, I decreased the limits of detection at the level that we were looking for.
Yeah. So, do you think that this procedure of iron removal will work also with cosmetics or something like that? I mean, for example, eyebrows or powders or something like that.
I don't know.
You know that in some cosmetics maybe they ask to detect cobalt, for example, and you have a lot of iron inside.
You have a very interference there.
Yeah. So my question is that if you ever try to get rid of iron in that way, in order
the only thing is that you have to try, because I'm not sure if for instance, in the cosmetics matrix, there is something that can influence on the formation of the complex. You know, perhaps now I cannot remember, but I think that also the pH is important. So then you have to do some test with the cosmetics matrix, because I'm not sure, but it could be an idea, because
because it's a big issue if you want to determine, for example, cobalt or something like that.
Yeah.
Right. Okay. Thank you very much.
Yeah, you're welcome.
Okay. Are there more questions? Now is the chance. I have one more question for the synthetic rainwater. Was it just water adjusted to pH and concentration of the sulfuric acid, or were there more components in there? So like organics maybe, or whatever. I don't know what the composition of rainwater is actually.
Yeah. Well, in this case, this study was done in a frame of a PhD of a student that was in our that it was a geologist study. Sorry. And finally, we decide we use only the sulfuric, because it was the main matrix. So we didn't include anything else. But I think that she previously made a study about the real composition, and then we decide to do like this.
Okay.
Yeah.
So I look on the list. I do not see any more questions.
Okay, and only I want to say something that is Merry Christmas to anybody, because I think that, because I think that we will not be able to say this face to face, so it's a good opportunity today to wish you Merry Christmas and a nice holidays. Yeah.